Hello, my friends of Hatari Labs. My name is Saul Montoya. Please welcome to this webinar. This webinar is about the regional groundwater modeling with a Voronoi mesh with MODFLOW6 DISV and Flopy. Okay, so in this class, we are going to explore the new, what is the new uh, package that we have developed to create Voronoi meshes and to how to create models based on those packages. Okay, so this is the link to download the data. So you have to do here, and then the password is Hatari Labs. Hatari Labs. Okay, great. So here we open the file, and then we extract here, okay, and then we place this under documents. Okay, so the webinar will be will start from the from analyzing defining the watershed a channel network, and from that we are going to create the mesh grid, and and in order to create the mesh grid, we are going to extract the vertices in order to create the model. Okay, I'm going to do first. I'm going to do here first a definition, okay, of the a quick example of the aquifer app to determine the channel network and the catchment areas. Okay, so this is really quick, and okay, so I am going to do that, and after that we are going to do all the stuff all together. Okay, so this part, just follow me please, and then we are going to do all the stuff later on all together. Okay, if you are following me through here, please type 1. So we type utils.hatarilabs.com. I am logged in, continue. Okay, you have to create an account here. It's free. I mean, this, so you create a new project, AA. Okay, you enter here, and then you have an util for the watershed delineation. Okay, you have to insert a DEM file. Which is the DEM file? The DEM file that is on the webinar. On raster, you have the DEM. Okay. And then you have the flow direction, the flow accumulation. And then you go to next. And then you define the 2,500, I guess, is the accumulation, the amount of cell for the accumulation. Okay, so here we define, we have defined the accumulation, and then we just do click here to define the output. Okay, and that's it, and then we go to download. Okay, once you have it downloaded, okay, the basin files, you extract here, and it gives you the MNT. You have the aquifer Hatari utils, you have the shape file, you have the catchment, the river basin, and the river network. Okay, these are the shape files. Okay, so it's really easy. Now, what you have there is the same that you have on the webinar folder. Okay, so is the catchment, the river basin, and the river network. Okay, if you are following me through here, please type 2. If you are following me through here, please type 2. If you have any questions, let me know. Okay, so everybody, let's start Anaconda. Anaconda prompt. Okay. See the documents, see the webinar. Okay, and here we launch Jupyter Lab. Everybody, please launch Jupyter Lab here. Okay, so okay, great. So first we are going to, okay, we are going to create a new notebook here that is going to call webinar. Okay, rename. Great. So there are some issues, okay, that you might have seen. There are some issues with the uh, the Jupyter Notebook, that it has a lot of warnings. Okay, it gave you a lot of warnings, and sometimes these warnings are annoying. Okay, first we need to install pip install mf6 Voronoi. Okay, that is the package that we are going to install. Okay, once you have installed it, please type 3, and we are in the version 0.6. Okay, so we have already installed. Okay, if you have installed mf6 Voronoi, please type 3. Okay, only Victor is here with me. Who else? Anybody has some problems? Okay, only Victor is here with me. For the people that are following from Chile, we have made the arrangements to give a course in May in the Siren, I guess is that the name of the institution. Okay, so it will be an open course, free, on MODFLOW6. Okay, so I hope that for the people in Chile, that you can make the arrangement for, because it will be on with invitation. But if you say, I mean, if you put that Python and Flopy, okay, you are going to get it. But I mean, we have to do that because we cannot risk for the course to be given to people without a MODFLOW background or Python background. Okay, only Ronnie and Victor are here with me. If anybody has some problem, let me know. This is my WhatsApp number. If you have any impeding problem that cannot be uh, solved. Okay, well, let's see. Okay, so we are going to say import warnings. Okay, so warnings dot filter warnings ignore. Okay, so I say Lester say I missed a step to get the file from. No, it's the URL is utils.hatarilabs.com. hatarilabs.com. And the file that you have to upload is this file, the one that is on this one, this file. Okay, Lester? Okay, import OS, import geopandas. Ajá. Geopandas as GPD. Ajá. From MX6 Voronoi, GeoVoronoi, import create Voronoi from MF6 Voronoi dot. No, the geoutils are actually not. Okay. No, so we just need the create Voronoi. Okay. Warnings filter. Filter warning. Sorry, I don't know why it's my head today. So we are going to create a mesh. Vor mesh is equal to create Voronoi. Okay, and the mesh name will be regional model. Regional model. Okay. With the maximum refinement is equal to 250. And the multiplier is for the multiplier is for the multiplier is for the for some meshing stuff. It's a concept. Well, the multiplier right now is 1. Okay, so vor mesh dot add limit of the basin. Okay, and this is in the basin is HP catchment dot shp. Okay, so this will be the limit of the model, and vor mesh dot add layer river. Okay, and this is HP river basin dot HP. Okay, and the size here could be 50. Okay, because this will be the size of the cells on the river path. Okay, great. So say vor mesh dot generate. This is some process of the original and distributed. Vor mesh dot create point cloud. Okay, and there vor mesh dot generate Voronoi. Okay, so these are the required process in the sentence that are needed. Okay, great. So, oops, sorry. So it's doing a discretization for the river. It will be, since it has to go from 50 to 250, it will go 50, 100, 150, 200, and 250. These are the cell sizes, okay, of the progressive refinement. If you are following, okay, I know that some people are watching the video, but if you are following the concepts, please type 4. And if you are following the scripts as well, please type 4, okay? Okay, if you are following the video, please type 4. If you are following the concept, please type 4. Okay, great. So it's still running. I think that since I am doing the streaming, so is kind of really slow. Okay, if it has finished for you, please type 5. Okay, it took 92 seconds to create the refinement. It has 10,000 points, 12,000 points, and now it's generating the Voronoi mesh. If it has finished for you, please type 5. Okay. Okay, great. Lester, who has else finished the Voronoi meshes? Meshing? Please type 5 if you have finished the Voronoi meshing. Okay, who else? Who needs more time? Let me know. Okay, great. Nobody. Okay, so vor mesh is equal to get Voronoi as shapefile, get Voronoi of shapefile, and then we are going to put that the output path will be output. Okay, so this is where the Voronoi mesh will be stored. It's actually stored as a shapefile. Okay, so and here on output, it will create the shapefile. So this is the shapefile. Okay, great. So it has created the shapefile. Okay, so we want to see the mesh is equal to gpd read file of the file which of that is in output and is regional model.shapefile. Okay, great. So mesh dot plot, and this is the Voronoi mesh for your basin. Okay, and it's pretty heavy. Edge color is equal to none, just to show the no, no fill color. Let's see if fill color is an argument here. You can open with QAS as well. No. Yeah, okay, I'm going to open my QAS. I didn't want to do it here, but okay. Yeah, well, this is the Voronoi mesh. Color. Let's see if color is an argument. No. Okay, so I'm going to plot it in. Okay. I have some commands. Sorry. It's not necessary. So it will be FC is equal to crimson. Alpha is equal to 0.3 and edge color is equal to teal. Okay, this will improve the meshing because what I want is that you see the meshing. Okay, so this is the meshing that you have created. Awesome. You can also open that with QGIS. Okay, so now we are going to generate the arrangement of the cells, okay, in order to import that into MODFLOW. So I say import sys os from mf6 Voronoi dot mesh properties mesh properties, import mesh shape. Okay, great. So mesh is equal to mesh shape. Okay, where is it? Of output regional model.shapefile. Okay, so that is the mesh. And then we are going to say the grid properties, grid props is equal to mesh dot get grid prop disv. Okay, so we just have to do like this, and it will create the arrangements of the cells arrangements and the cell properties, the centroids, and so on. Okay, so that's it. If you are here with me, please type 5. If you are 6, 6, 6, 6. If you are following me through here, please type 6 as well. Mhm. Now we have to do the cell 2D is equal to grid props of cell 2D. The vertices is equal to grid props of vertices. Okay, the number of columns per layer is equal to grid props of numbers column per layer. Grid props invert. Okay, so this is the invert, and centroids is equal to grid props oops of centroids. Okay, great. So these are the, okay, so we have extracted all the information. So the vertices, all of these are arrays, okay? And then you can go to the Flopy documentation, to the MODFLOW documentation to see how is the arrangement of that. Okay, because it's pretty lengthy. Okay, so that is why we are not going to. Okay, but what I wanted to mention, okay, so what I want to mention is that these are the required data that you need for the creation of the grid in with the DSV discretization. Okay, so that is what is important. And my recommendation is that you go to the MODFLOW documentation in order to see what is exactly the arrangement and how this is created. Okay, great. So now it's time to create the model. So now it's time to create the model. Okay. So import rasterio, import numpy as np, import flowpy, import matplotlib.pyplot as plt. Questions? Is there any questions? Uh, no, 5 layers. Yep. Okay. The this grid is constant for all the layers. So we later on we are going to define the layers. Okay. Just in two cells. In the next cell we are going to after the next cell we are going to define the layers. Okay. The yeah the x and y. There is no set on centroids because in this V the grid is constant through all the layers. Okay. I guess that in this U the unsatisfactory grid the cells can change over with depth. Okay, but this is another case. Okay, so it's not okay, Voronoi meshes cannot be interpreted as unstructured grids. Okay. No, no. Mm, yeah. Okay, src is equal to rasterio dot open. Okay, so it's raster, and this is the raster, the T file that we have. Okay, and elevation is equal to x for x in src sample. Okay, centroids. Okay, so we from that we get the elevation for every cell. Okay, and that's it. Okay, so and now we define that lay is equal to 5. Okay, mtop is equal to mp array of lf0 for e and elevation in enumerate oops, sorry, in enumerate elevation, and set bot is equal to mp0s lay ncpl. Okay, so this is mtop is an array, okay, of the elevation, yeah, that, and is the, I mean, okay, if you're curious, okay, first, aquif inferior bottom is equal to 2800, set bot. I think that in the because this is how to say, this is kind of very time consuming. I think that I can get it, I can create it on the function that on the package that do that. Okay, let me know if this will be a good idea. Set bot 1 comma is equal to a quiff inferior bottom plus 0.85 times m top minus aquifer inferior bottom. Okay, and then so we are going to create a cross section here, and this cross section will show, yeah, the cross section will show the arrangement that we have created. Okay, Mhm. Okay, so far that's it. If you are here with me, please type 7. If you are following me through here, please type 7. Okay. Okay, so now we are going to say sim name is equal to mfsim, mf6 sim. Okay, model name mf6 model vs is equal to model files. Okay, and sim, let's create the sim flowpy.mf6.mf6 simulation of the sim name is equal to model name version is equal to mf6 xname is equal to bin, because the executable is here under bin, mf6.exe, and the sim vs is equal to model vs. Okay, so we create the if you're I think that the I think that the um, the package should make an example raster, an example of the different, okay, should create this, okay, should create this. Yeah, because actually this is the same for every project, mostly the same for every project that you are going to create ever. Okay, do you think, I mean, Lester, do you think that will be a great idea because it will decrease the amount of typing? Yeah. Yeah, it has to create this. Yeah, I'm thinking how to. I mean, what I think is that it's awesome to do that in Python. Okay, but what I want also is that you decrease the amount of typing. Okay, because do your models in Flopy actually imply that you type a lot. Okay, so let's create the GWF is equal to flowpy.mf6 dot modflow gwf sim model name is equal to model name and save flows is equal to true. Okay, and then we have, for example, the EMS is also the same. Flowpy.mx6.modflow EMS of sim the complexity is equal to complex. It's complex with on capital letters. Outer minimum is 100. Outer inner maximum is also 100. And linear acceleration is equal to big E stop. Okay, great. Sim dot register EMS package EMS of model. Okay, great. If you are following through here, please type 8. If you are following me through here, please type 8. Okay, because this is the same for every project as well. Now we create the DSV. Flopy.mf6.modflow gwf DSV of gwf of inlay is equal to inlay ncpl is equal to ncpl top is equal to mtop. Okay, bot m is equal to set bot. Okay, invert is equal to invert. Vertices is equal to vertices. And cell 2D is equal to cell 2D. Okay, invert. Okay, great. So we have created the invert, the vertices, and the cell 2D. Okay, great. Any questions? Okay, any questions? No. If you are following me through here, please type 9. IC is equal to flow pi. This is also the same for all the MODFLOW GWF IC of GWF starting point is equal to np dot stack of mtop for E in range of inlay. Okay, this is just a formatting. I mean, it's the same. Okay, but okay, so we need a value for every layer. Okay, that is why this is in top for E in range. Okay, if you are following me through here, please type 1. Inlay. If you are following me through here, please type 1. So what we have done is we have created the groundwater flow, the solver, the we have created already the discretization by vertex, the initial conditions, and we are going to um, create the cell type, the hydraulic conductivities. Okay. What is the, okay, great. So what is they asked me what is the set bot? The set bot is in ModFlow, you define the top, that is M top of model top in model muse, and then you have defined an array that defines the bottom of every layer. So this is set bot. So that is why set bot is an array, while M top is just one list. Okay, Diego? Okay, so let's continue. So let's see, kx is equal to 4a to the minus 4, 5a to the minus 6, 1a to the minus 6, 9a to the minus 7, 5a to the minus 7. So these are the hydraulic conductivities. And if you see that the hydraulic conductivities are decreasing with depth, okay, we have 5 layers. Is cell type is 1, 1, 0, 0, 0. Okay. And the MPF is equal to flowpy.mf6 dot modflow gwf npf gwf npf of gwf, and it has the xt 3D options. Okay, it has that. Okay, I don't think that it's doing much here, but it's here. Save a specific discharge is equal to true. Okay, cell type is equal to cell type, and k is equal to kx, and close. Great, so that's it. Okay, if you are following me through here, please type 2. Okay, so the storage will be flowpy.mf6 dot modflow gwf stow of the module gwf, convert is equal to 1, steady state is equal to, okay, 0 is equal to true, comma, and then we can close this as well. Okay, so we are just saying that this is, what is the error here? Is ampere. So we don't have the ampere. Let me check this. Oh, yes, 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 yes. Before the GWF, we need to install the TDIS RC. tdis is equal to flowpy.mf6 dot modflow tdis of sim name is equal to tdis time units is equal to days. Okay, and then say period data is equal to this RC. Okay, so this is the temporal discretization. Since we have created and then we have inserted here, so we need to restart the kernel and run all cells. Okay, because this is dependent on the order, so it has to be here in order for the other package to recognize the number of periods. Okay, so if you are following me through here, please type 3. If you are following me through here, please type 3. Okay, it's taking time because it's actually doing the Voronoi meshing from the beginning. Sorry. Okay, so okay, let's see. It's still okay. This is the storage. Okay, great. If you are here with me, please type 4. It has finished for me. If you are here, please type 4. Great. So now we are going to do recharge is equal to 0.15 times 365 times 8500. Okay, so recharge package. So it's 150 millimeters per day, flowpy dot mf6 dot modflow modflow gwf rcha of gwf of recharge is equal to recharge rate. Okay, let's see what happens here. Okay, great. So, and for the evapotranspiration R recharge rate is 1.365 times EVT is equal to flow by dot ml6 dot modflow GWF EVTA of GWF of IEVT is equal to 1. Surface, this is the evaporation surface, is M top. The rate is equal to EVTR, and the depth is equal to 1. Okay, great. Okay, if you are here with me, please type 5. Okay, so we have defined the... Now we have to define the intersect, and the intersect is a great tool from Flopy that allows you to intersect shapefiles to the grid, and it works with all type of grids. So let's say inter ix is equal to flowpy.utils.grid intersect.grid intersect of the model grid. Okay, that is great. Okay, so from shapely geometry import multi-line string. Okay, great. So let's open. Reverse is equal to gpd.read file of hfp river basin .hfp. Okay, so now we are going to, insert the river shape file. Okay, so we are going to insert the river shape file as the shape file for the as the drains. Okay, as the drain package. Okay, so the intersect is a tool, okay, where you insert the grid, okay, and then you are going to see how you can have a shapefile, or like is for the drains, or is for the source, contaminant source, okay, and it will give you the cells that intersect with that shapefile, the cells of the grid that intersect to that shapefile. Is that okay, Sai? Okay, so I say list rivers is equal to, okay, for E in range of rivers shape 0, okay, because there are many river paths, okay, list rivers dot append rivers geometry dot log. Okay, just to mention that we have a coming, okay, so hatarilabs.com, we have a coming course in MODFLOW6, okay, yeah, hatarilabs.com. Okay, so we have a coming course in MODFLOW6, that is this one, yeah, and this is the link. Okay, so if you want to know, and this is the basis of MODFLOW or Flopy, MODFLOW6 and Flopy, okay, for any course, okay, because we are going to do a lot of stuff and apply stuff in groundwater modeling, okay. So if you want to know all the stuff about how Flowpy works with ModFlow6, all the stuff, I mean, more examples about the intersection, I will strongly recommend that you take this course because it's a live opportunity where you are going to learn, and then you are going to discuss, and then you are going to practice creating Flowpy um, codes that create ModFlow6 models, okay? So take advantage of this because actually the next time that this course will be given, maybe will be in 3 years when the Flowpy code actually will change dramatically, okay? So that is the only time that this course will be given. Okay, thank you. So let's see. So river MLS is equal to multi-line string of lines is equal to list rivers. Okay, so what is a multi-line string? And a string is something that is the multi-line is something from Shapely. Actually, doesn't exist in normal GIS, okay? So, but these are conversions that we need to create to do it's just to join all the rivers. So river cells is equal to ix dot intersect, okay, of river MLS of cell IDs. So river cells, okay, so we can point the first 10 cells of the model, yeah, more rivers. What is rivers here? Rivers. This is river, sorry. Okay, so these are the first 10 cells, okay? That is great. Okay, if you are here with me, please type 6. If you are here with me, please type 6. If you are following me through here, please type 6. Okay, great. So now we have the river cells, and now we say river SPD okay. So the river SPD0 will be an empty. So for cell in river cells is equal to river SPD of 0 dot append, okay, of 0 comma cell and top of cell and the 0.001. Okay, so when you, because the river will be treated as a as drained, because in our conceptualization the river network only gains water from the groundwater. Okay, the groundwater discharges to the river system. This is equal to flowpi of mx6 dot modflow gwf drn of gwf stress period data is equal to river SPD. Okay, great. Okay, so we can plot our river. Why not? Ref plot of MFLA is equal to 0. Okay, so this is our river network. Okay, pretty interesting. Already intersected from the shapefile that comes from. Okay, so the river network is intersected from the shapefile that come from the utils.labs, the watershed tool. Okay, so it's pretty impressive that we have done that in just, well, 1 hour of class, but okay, so it's something complete. Okay, so if you are following me through here, please type 7. Okay, so we say OC is equal to flowpi dot mf6 dot modflow gwf OC of gwf. Okay, head file record is equal to f. It has this strange format. gwf name dot hds save record head. Okay, if you are here with me, please type 8. Okay, so sim.write simulation, sim.run simulation. Okay, so now it's running. Okay, great. If you are here with me, please type 8. Okay, great.
Los libros que orgánicamente se habían vendido ya más.
Okay, so it's running. Yeah, and the problem is that is okay, it takes some time because it's not getting convergences. Okay, so that is the problem. Okay, it should be faster. Okay, if it's but this is a work to do because we have to see what is the real deal here. Mhm. Um, but okay, these will be topics for other parts. If it has finished running for you, please type 9. If it has finished running for you, please type 9. Okay, Lester, has it uh, does it found the non-convergences or it ran okay for you? Let me know. Yeah. Mhm. Yeah, I have to see what is going on there. Well, one step at a time. Mhm. For me, it's taking long. Mhm. Well, let's type in the list. Okay, let's start typing what is next about this. Okay, so we need to do a head obj is equal to gwf dot output head. Okay, and then we get the head obj. The we can get the kst p k pair. Okay, great. So we got this. Okay, so this will bring the. Okay, so then we need the date. The heads is equal to. Okay, by default is the last one, but there is only one. Head obj dot get data. So heads. So we can plot for the second stress period 0,5. Okay, so this is just to plot some heads. Okay, and finally fig is equal, which is Lester, which is your with your processor? Let me know. Let figure of fig size is equal to 12,8. Oh, okay, yeah. So we can, okay, we can say AX heads. Okay, great. So these are the heads. By default, these are non-values. Okay, so AX is equal to fig at subplot 111 aspect is equal to equal. Okay, model map is equal to flowpy dot plot dot load map view. Model is equal to GWF. Okay, so and then we are going to plot the cells on the third layer. Ah, okay, okay. Yeah, because I am with a, yeah, my computer is what is it? E5. Okay, so that is the main difference. Okay, as you have seen the difference with my friend Lester. Okay, he has a better processor. Yeah, and that makes a difference. Okay, so we can say cell head is equal to model map plot array of heads 3. AX is equal to AX, CMAP is equal to blues alpha is equal to 0.8. Okay, and then say line collection is equal to model map dot plot grid. Okay, just because I want to see the grid of line width is equal to 0.3 and alpha is equal to 0.5. PLT dot color bar of cell head and shrink is equal to 0.75. And that's it. Okay, my friends, this is the result. Okay. Wow. Yes. Okay, that is not what is supposed to be because Lester is this is really an error. Okay, so and this can be due to the okay, if you see on the this is the okay, if you open this webinar, this is the no the if you open the regional model, that is the file, okay, you will see that the that it has created the error and the contours at the head, okay, and these are really logical, okay. However, this is with the discretization of on the discretization of the is 100, so it goes from 250 to 100, while here that it went from 250 to 50, it has those problems. Okay, well, still more to go on. Okay, I won't run it to from the beginning with, but you can run again to 100 and see if if you get a better results. Okay, if you are following me through here, please type 1, and if you have another questions, let me know. Otherwise, just say the city from where you're connecting and which topic, if you have any topic to follow incoming. If you have any other topic to follow incoming webinars, okay, let me know that as well. Okay, if you have any questions, or if you don't have any questions, just say good night and the city from where you are connecting. And okay, for the